Okay, next we are going to solve the chapter 3 system of linear equation by Cholesky method. Cholesky method is one of the LU decomposition methods. Okay, for a linear system AX equal to B, okay, we can decompose K matrix A into lower LU, where the L is lower triangular matrix. Here, only lower part consists of value, and U is the upper triangular matrix, only upper part consists of value. Okay, lower part here is 0. L is upper part consists of 0. Then first step, find for L and U, and then from A equal to LU, then we have LUX equal to B, and then let UX equal to Y. Then we solve LY equal to B by forward substitution. Step 3, from UX equal to Y, we solve X by backward substitution. Here, we have AX equal to B. A is LU. So this is step 1. Find L and U. And then let UX equal to Y. So second step, solve Y from LY equal to B. Lastly, UX equal to Y. Solve for X. Okay, that is step 3. Okay, we have 4 types of LU decomposition methods here. The first one is Doolittle, where diagonal of L is 1, because Doolittle have L here. Crowd U, so diagonal of U is 1. Thomas, where the A must be 3 diagonal. In the A is only, okay, have main diagonal 1 row, below diagonal upper triangle, upper you got 1 row, so 3 diagonal. And the U for Thomas method is actually diagonal of U is 1. Cholesky, where the A must be symmetric positive definite, where the U is L transpose because they are symmetric. So U is L transpose. Okay, we can prove a matrix A is symmetric positive definite using definition if X transpose AX is positive for any X which is not equal to 0. Okay, for example, show that matrix A equal to 9, 0, negative 1, 0, 2, 0, negative 1, 0, 8 is symmetric positive definite using definitions. Okay, so using definition, okay, we have to show that X transpose AX, where this is a matrix A, X initially is a column vector, transpose it become row vector. So A is a 3 by 3 system. Vector X is 3 by 1. So 3 equal to 3, they can be multiplied. The result is a 3 by 1 vector here. First of all, I multiply A with X first. So we have a first row times first column. So the result is here. 9x1, 0 times x2 is 0. So negative 1 times x3, which is negative x3. Okay, second row times first column. So you have 2x2. Okay, lastly, negative 1 times x1, 0 times x2, 8 times x3. So 8x3. So this is a X transpose 1 row times 3 column. If 3 equal to the row 3 here, so it can be multiplied. The result is actually you have 1 by 1 matrix. So we take here first row times first column. The result actually only 1 by 1. Here. And so this one. In x1, multiply 9x1 minus x3, x2 times 2x2, x3 multiply negative x1 plus 8x3. Expand and simplify it. Here 9x1 squared, this is 2x2 squared. Okay, you have 8x3 squared. Okay, 9, 2, 8 are positive. anything that's squared, okay, so negative will become positive. So the first three terms are always positive, okay, and then we have here negative x1, x3, okay, with this one, so total is negative 2x1, x3. Okay, to make sure that this term is always positive, we make it become bracket x1 minus x3 squared. So when you expand, this will be x1 squared minus 2x1 x3 plus x3 squared. So minus k 2x1 x3, so it's here. So we have x1 squared, initially is 9, so you need to add up 8 more. Okay, so 2x2 is here. So here, this the first term here, when expand, you already have 1 x3 squared. Total is 8, so we need 7 more. So the first term, when we squared, we're always positive. The last three term is always positive. So it is proven that X transpose AX is positive. Hence, this matrix A is symmetric positive definite by the definitions. Second, we can show that matrix A is symmetric positive definite using the rule. First rule is A must be non-singular, means determinant of A cannot be equal to 0. Second one is easy, which AII, which is the diagonal value, is always positive. The third one is maximum of magnitude of AKJ less than or equal to maximum of the AII. Okay, mean the maximum of non-diagonal value, the maximum of the magnitude of the non-diagonal value is always less than or equal to the maximum of the diagonal value. Okay, number 4 is AIJ squared less than or equal to AII AJJ. Okay, we use back the same metric to and then prove it by using rules. This is, I think, this is definition of rule. Let me check. Using rules. Definition is just now. Okay, using rule. Okay, then, so first rule, you have to, shows that determinant of matrix A is not 0. Okay. Okay, we can go to the matrix mode number 4 to easily find the determinant of matrix 3 by 3. This model can up to 4 by 4. So 9, 0, negative 1, 0, 2, 0, negative 1, 0. Easy to clear. Go to options. Go down. Determinant number 2. Okay. Option. Pick number 3 for matrix A. Close the bracket. And we get the determinant of the matrix A here is 1, 4, 2. 1, 4, 2. Okay. And then by the second rules, you must prove that the diagonal value is positive. Okay, A11 is positive, A22 is positive, A33 is positive. So the second rule is satisfied. The third rule, the maximum of AKJ, maximum magnitude AKJ means is non-diagonal value, which is 1. The maximum of the diagonal value, which is 9, which is true. Okay, fourth, you have to show that AIJ squared less than AII AJJ. Okay, we take this entry, A12. Okay, since they are symmetric, A12 symmetric with A21. Okay, the squared is 0 squared equal to 0. Okay, less than A11, A22, which is 9 times 2 equal to 18, which is true. And then we take A13. Yeah. Equal to A31 squared, which is negative 1 squared, which is 1, less than A11, A33, which is 9 times 8, which is 72. Mean 1 is less than 72, which is true. Okay, lastly, A23 squared equal to A32 squared, which is 0 squared equal to 0, less than A22, A33, which is 2 times 8 equal to 16. So it is true 0 less than 16. Hence, by rule, we have shown that determinant of matrix A is non-zero. Magnitude AII is 0. AII is positive. Maximum magnitude of AKJ is less than or equal to maximum AII. AIJ squared is less than AII AJJ. Hence, matrix A is symmetric positive definite. It must satisfy these 4 criteria. Okay, and then thirdly, we can show that if a symmetric matrix A is positive definite, first they must symmetric respect to diagonal, and if it is positive definite, if and only if each of its leading principal sub-matrices has a positive determinant. Okay, we show back the same matrix A is symmetric positive definite using theorem. Okay, where determinant of A1, actually determinant of this 9 is, this is equal to 9. Determinant of 9 is 9, which is positive. Determinant of A2, which is 9 times 2, minus 0 times 0, which is 18, also positive. Determinant of A3, just now we found, which is 1, 4, 2. Okay. Since determinant of A1, A2, A3 all are positive, hence A is symmetric positive definite using theorem. I think using theorem is the easiest compared to the second easiest will be the using rule, where you shows that diagonal value is positive, determinant not equal to 0. Okay, the maximum of magnitude which is not from diagonal is always less than or equal to the magnitude of the maximum of the diagonal value, and then AKJ, AIJ squared less than AII times AJJ. Okay, the most difficult is and you need algebraic expansion and simplification to show that X transpose AX, which is positive. This is using the Kate definition. Okay, now we're looking at Cholesky method. To use Cholesky method, make sure matrix A must be symmetric positive definite. Then from A equal to LU, solve for L and U, where the U is actually L transpose. So A equal to LU, so LUX equal to B. Step 2, solve LY. UX here equal to Y. Solve LY equal to B for Y using forwards, and then UX equal to Y, solve it using backward substitution. Okay, example, solve this linear system using Cholesky method. Okay, step 1, we need to find L and U, where the U is actually L transpose. Okay, L is a lower triangular matrix, so we let it become A, B, C, D, E, F. U is actually L transpose, so it transpose first column become first row, second column become second row, third column become third row, and then you do matrix multiplication to get this one. Okay, for example, now slowly show you. First row, this is 3 by 3, 3 by 3, 3 equal to 3 here can be multiplied. The resultant matrix is 3 by 3. So now first row times first column, so have A times A squared. Okay, then we okay, and then we move to now first row times second column, so A times B. 0 times C is 0, 0 times 0, so is AB. Yeah. And then we move to third column. So first row times third column, so AD. And they are actually symmetrics. Symmetrics. I can slowly see it. Okay, now second row, first column. So it's AB. That's why you see this one and this one symmetric. And move to second column. B times B squared. Okay, here B times B plus C times C, 0 times 0. So B squared plus C squared. Okay, lastly, we move to third column, second row, third column. So B times D plus CE. 0 times L is 0. So BD plus CE. And it's also, this one should be symmetric. Okay, let me show you. So we erase first. Now we move to third row. Okay. I start with third row, third column. So D times D, D squared. E times E plus E squared, F times F plus F squared here. Okay, now I erase it. Let's move to second column. So you have B times D, CE, 0 times F is 0. So BD plus CE. So they are actually symmetrics. Okay, this one will be symmetric with this. Okay, let's move to first column. First column have AB because this one 0, this one 0. AD. So you can see product of your L with LU is actually symmetrics. AB has AD, BD plus CE, BD plus CE. Okay. So we have found the metric multiplication of A equal to LU. Okay, where the U is actually L transpose. Okay, so now we are going to compare left side with right hand side. So we have here, compare, first row, first column, A squared equal to 9, A will be 9, we take positive value, which is 3. Okay, and then here, second row, first row, second column, A, B equal to 0, hence B equal to 0. Because A not 0, only B become 0. And then here, first row, third column, A, D equal to -1, hence D is -1/3. Okay, this is symmetric, so you go to here. Second row, second column, B squared plus C squared, B squared plus C squared. Here, equal to 2. Since B squared is 0, that's why C is actually 2. Take positive. Okay, lastly, BD plus CE equal to 0. So you have BD plus CE equal to 0. Plug in B0. So this term 0. Okay, C times E is 0 provided E equal to 0 because C not 0. Hence only E is 0. So lastly, the last K value, which is D squared plus E squared plus F squared. You see according to the 3 by 3 here. D squared plus E squared plus F squared equal to 8. Okay. D is 1/3, negative 1/3, so square it 1/9. E is 0, this is 0, so plus F squared equal to 8. So F is actually 8 minus 1/9, F squared 71/9. So F is actually 71/9 positive. Okay, or you can equate to 2.8087. Okay, so A is 3, B is 0, D is negative 1/3, C is 2, E is 0, F is 2.8087. So we have completed the first step. This is the L, this is U equal to L transpose. Now we move to second step. From Ly equal to B, solve for Y by forward substitution. So put up this one L from here. Y that you're going to solve equal to B. B obtained from the original equations. And then you can input this Ly equal to B, Ly equal to B into your equation mode in calculator. Then you can easily obtain Y1, Y2, Y3. Okay. So means you can move to equation modes. Yeah, equation mode. Okay, simultaneous equation is number 1. We got 3 unknowns. So key in the Ly equal to B. 0, 0. Row by row. 3. So 0, 2, 0. This is 5. Negative 1 divide 3. 0. 2.8087. 6. So you get X is actually the Y1, 1. Y is actually the Y2, 3.5355. Okay. Z is 2.2549, which is the Y3. Okay. This is directly using equation mode, okay? Or if you want to solve it using forward substitution, mean forward, okay, mean from first equation, you have 3y1 equal to 3. That's why y1 equal to 1. Okay, and then from second equation, okay, set2 y2 equal to 5. Once you can find the y2, which is 5 over set2. Okay, lastly, the last equation, negative 1/3 y1 plus 2.8087 y3 equal to 6. Then you find for your y3, which is 6 plus 1/3 y1 minus 2.8087 y3. Okay. So you want to find y3 on. Okay, the y3 that we are going to find. So mean y3 is 6 plus 1/3 y1. Okay, and then divide 2.8087. Okay, plug in y1 from here. So this is by manually calculate using forward substitution. Okay, just now what I show is I actually directly key in the system Ly equal to B to obtain the y quickly. Okay, and then from this is A equal to Lu. Step 3, solve Ux equal to y. Okay, this U, okay, X equal to y they obtain. This y they obtain in step 2. Okay, and then also I use the calculator, the equation mode. And now I input the system Ux equal to y, which is 3, 0, negative 1 divide 3 equal to 1, mean row by row, 0, third 2, 0, 3.5355, and then 0, 0, 2.8087, 2.2549. So I obtain X, which is X1 0.4225. The Y is actually the X2 2.5. Z is 0.8028. Okay, this one, I didn't use backward substitution. I directly key in Ux equal to y into the system. Okay, if you want backward, it's actually from the last equation. Okay, from the last equation, you have 2.8087 x3 equal to 2.2549. Then your x3 is 2.2549 divided by 2.8087. And then from the second equation, set to x2 equal to 3.5355. Then the x2 is 3.5355. Lastly, from the first equation, 3x1 minus 1/3 x3 equal to 1. Okay, and then you solve for your x1. Plus 1/3 x3 divided by 3. Okay, this is by backward, means start from the last equation. Step 2 is forward because start from the first equation. Okay, and the answer they obtain, you can always double check with the initial system using equation mode again, where the system is 9, 0, negative 1, 3, this 0, 2, 0, 5, negative 1, 0, 8, 6, 4225, okay, 2.5, which is 8028. And this is from the original system. Okay, so I repeat again, basically to solve using Cholesky method, make sure the matrix A is symmetric positive definite. Then step 1, find for L and U, which is L transpose. After that, step 2, Ly equal to B, solve for Y using forward substitution, or you can use the equation mode to solve for your vector Y. Step 3, from Ux equal to Y, solve for X by backward substitution, manually, or you key in Ux equal to Y in the equation mode in your calculator, then you can obtain the vector X easily. And then you can always double check using the original system into the equation mode. They must obtain the same answer with the step 3 in Cholesky methods. Okay, and then we conclude back. So we have 3 ways to show that A is positive, symmetric positive definite using definition, which is have to show X transpose AX is positive. Okay, and then second one, using rule, show that A is non-singular where determinant not equal to 0, and then AII is positive, maximum A magnitude AKJ less than or equal to maximum magnitude AII, and then the AIJ squared less than AII AJJ. Okay, and using theorem, basically the principal submatrices has a positive determinant. Okay, with this, thank you for your attention.